Hi guys, so today I'm going to tell you more about supervised learning, and we're going to focus on regression and classification using Python Jupyter Notebook. If you have not yet subscribed to my Facebook page and YouTube channel, kindly do so in order for you to follow exciting content like this. Also, a lot of people have been reaching out to me to discuss about the possible way of diving into AI. I'm available for mentoring, so if you want some mentoring on how to go about your career journey into AI, do well to reach out to me and I will be happy to guide you in this journey. So, what will you be learning today? Today, I'm going to be telling you about supervised learning techniques in detail. I'm also going to tell you about some of the key supervised learning algorithms and also hand-on example of regression and classification using Python Jupyter Notebook. So, the prerequisite for this course is for you to have been able to install Python in your PC and also Jupyter Notebook in your PC. If you don't know how to go about this installation, kindly refer back to our previous video on this installation process and then you could be good to go. So without further ado, what is supervised learning technique? Supervised learning technique is that branch of AI that focuses on training the machine learning algorithm based on input features and also a target or labeled training data set. Now, the goal of the supervised learning technique is to make prediction on an unseen data set. Now, consider yourself as a student in a classroom. The teacher is going to teach you on a particular subject matter. Usually, the training or the teaching phase is longer than the evaluation phase. After the teaching phase, the teacher is going to rank you or rate you on different skills depending on what the institution is using. In same manner, if we have a data set that contains tomato, bell pepper, carrots, we have the characteristic of each of those fruit. We fit this characteristic and also the label to the machine learning algorithm, and then at the end of the day we will make prediction to see if the machine learning algorithm can be able to deduce between a bell pepper, a tomato, or a carrot. So usually the training phase takes large chunk of your data set, usually from 70% to 90%, while the testing phase take a little portion of your data set. Another note that I want you to get here is during training you feed your algorithms with the target set and also with the input features, while during testing you only feed the trained algorithms with your input features and withhold the target features. However, you will use the target features to be able to make evaluation to see how well your model have learned from the training phase. There are two types of supervised learning techniques. There is the regression techniques and also there is the classification techniques. The regression techniques focus on dealing with regression problem. Regression problem are usually problems that has to do with continuous variables. We usually have the response variable and also the explanatory variables that we could estimate them on a straight line or depending on the complexity of the problem. Then the classification phase usually deals with categorical variables, which has to do with categories and also probabilistic in nature. A good example is an email spam, or it's not going to be spam, it's going to be cancer, or it's not going to be cancer. While a good example of a regression problem, the housing problem we stated last time, and also problems that has to do with continuous variables. This all falls into regression problem. Now, a common example of supervised learning algorithms or in regression, we have the linear regression. The linear regression is usually the simplistic model in the regression algorithms. We also have the decision tree, and we also have the random forest. Now, I want to make a note here that the more complex the problem becomes, the more difficult it becomes to evaluate the model using a linear model. So that's what gives rise to the other algorithms like the decision tree and random forest you see. Now, the regression problem usually look like this. You all know the famous regression equation where we have y equal to beta naught plus beta 1 x1 plus the error term. So usually beta naught is the intercept, and then the x are the explanatory variable, and beta 1 and beta 2 are the coefficients of regression, and then we have different assumptions that follow. Then the regression problem could be simple regression. It could also be multiple linear regression. Usually the multiple regression problem has to do with when we have so many response or so many explanatory variables, then we classify it to be multiple problem. Then the decision tree. In the case of the decision tree, we talk about information gain and some sort of entropy. Then we talk about splitting this based on this information gain. So if it's greater than or less than that particular threshold, we split it based from the root node and then down to the decision nodes, and so on and so forth. Now, a good example of a classification problem is the logistic regression. The logistic regression again is the simplest example of classification problem. Now, the logistic regression came up because the normal linear regression could not solve some problems, so the sigmoid function was used to help us to be able to deal with some of those problems that we could not be able to handle. Now, that's a long process that I would want us to dive into. Another example of classification problem is the support vector machine. The support vector machine introduces the concept of kernels and also hyperplane and support vectors. So using the margins, we would be able to divide this futures or data points into different margins, and then we could be able to minimize this margin. And when we looked at how close or far these support vectors are, we could be able to arrive at the decisions on this. We also talk about decision tree in the regression problem in the previous slide. You will see that when we have so many of these decision trees assembled together or combined together using some sort of bagging approach, we talk about a random forest. Now, the random forest is the combination of several decision trees put together, and then using a majority voting kind of approach, you'll be able to come up with a decision. Now, I want you to also understand there are other examples like the k-nearest neighbor that uses the concept of neighborhood and to classify or to be able to split the data set. So there are several other examples like the XGBoost and also different other classification algorithms that is being developed every day, but these are like the most popular ones that we use in our everyday tasks. Lastly, I want us to go into the hand-on sections practical using Python Drital Notebook. So the first example we're going to look into is the regression problem, where we'll be predicting housing prices using the Boston housing dataset. Now, this dataset, you can be able to download it following this GitHub link, and you can download it in CSV file format. The second problem we're going to look at is a classification problem that has to do with breast cancer. Now, the goal of this project is for us to develop and evaluate a machine learning model that can accurately classify breast tumor and classifying it into malignant or a benign cancer. So we will be given some sort of input futures, and then we will now be able to run these futures. So let's start from the first one, which is classification problem. So first of all, you load the data set. So you will be required to make some installations. You will need to install pandas, numpy, skitlearn, and so on and so forth, cbon, matplotlib. Then next is different features of this particular data set. We have the target variable here is the mediv. So the first thing you do is to load the dataset. When you load this dataset, you run it, and then the next thing you're going to do is to ensure, if you cannot be able to run this dataset using the GitHub, ensure that you try to download the dataset directly. So the next thing is we check for the different characteristics of the dataset. We check for missing values. We check we also check for the descriptive statistics. So this will help us to be able to know the distribution of the dataset, the mean, max, if there are outliers, the percentiles, etc. Next, we visualize the dataset by plotting a histogram on the continuous variable. Remember, I highlighted that in regression problem we're dealing with continuous variable. So you could see that most of the features are skewed to the left. However, that's fine. The target variable, it's a bit normally distributed, kind of. So the next thing we check for outliers using the box plot. The box plot is a very good plot that you could use to check for the presence of outliers, although it's not very important for this study. The next thing we do is to plot a scattered plot to be able to see some of the relationship that exists between the features and the target variable. Next, we visualize correlation. We wanted to see if there are presence of multicollinearity, although that's not a priority in this case, but you could be able to check one of these variables are actually showing multicollinearity. So in order for you to improve the features, you could do some feature selection by removing one of the features so they don't compete with each other. So now we have finished the exploratory data analysis phase, EDA. Next for us to do is to begin the modeling phase. So we split the data into training and testing. Now if you see the splitting, we split it into 80% training and 20% testing. So next we now train the dataset and then we evaluate the dataset on the testing. Now when you looked at it, you could see the linear regression actually scored quite high but not that great. So we will now use complex models to evaluate the problem. Now one of the things I want to make emphasis on is you don't have to use just one model. Try several models and then you could pick the best model that evaluates the problem. So next, using the decision tree, you could see the performance improved drastically compared to when we were using linear regression, and you could actually see it actually evaluated the problem much better than the linear regression did. And then next we want to visualize the decision tree to see how the root nodes is. So actually we could see how the root nodes are splitting. So if it's greater than or less than this, it falls into the left or the right. So these are the decision nodes and also the entropy, like I said in my video. So the next one we did was to use a random forest model. So again, we trained the random forest to see, you could see actually the R square shows 89%, which is quite better compared to decision tree, which was around 85, and linear regression model was I think around 70. So you could see the more complex model you use, the more it evaluates the problem better. So you can see in the regression phase, we use tree model. We use a linear regression, we use the decision tree, and also the random forest model to evaluate the problem. Now we are going to, so in the classification example, we are using a dataset on cancer digitalized image, and it has several features, and target variable is going to be if it's a tumor or malignant, or if it's benign, that's not cancer. So there are several features that we're going to be using. So the same thing that we did during the regression phase, we're going to perform some EDA, and we're going to check for missing, and then we'll go to the modeling phase. And again, we're going to start with the simple model, logistic regression, then we move to more complex model, and then we see how the performances are being evaluated. So there are different performance metrics that we could use. In regression problem, you usually use the R square to see the performance, while in classification you have several other performance measures like the accuracy, the precision, recall, F1 score, and so on. So the dataset link is from GitHub. Again, you could pull this dataset, or again you could download it straight to your PC, and then you could import it into your PC. So looking at the characteristics of the dataset, all the dataset, most of them are integers, and there is a bit of float. Now there is this dataset that has missing value, about 16 of them. So it means we have to handle these missing values, else we will run into issues. So we check again for the descriptive statistics to see different features of the dataset. So next we visualize the dataset, performing some EDA to see how the data is distributed. Most of the data again is categorical, so because it's categorical variable, we don't need to do histogram. In this case, we used bar charts to see the distribution. Then again, we check to see for outliers, which again is not a priority for this problem. But next, we need to handle the missing value. Now there are so many approaches that you could use to handle missing values. One of the approach to handling that you could use for the missing values is to use the mean, the median, and so on and so forth. So, but in this case, we are going to use the median to handle the missing value. So the first model we are training is the logistic regression. Again, the classification, the accuracy is around 96, and we have the F1 score. Now it's not always that the accuracy is the best measure. Whenever we have imbalance problem, it means you have to explore other performance measures like the confusion matrix or the F1 score. Now we also look at the K nearest neighbor, which also did very well, and it actually performed better, around 97, a bit up from the simple logistic regression. And support vector also did well compared to the logistic regression model. So next we also evaluate the random forest, and you could actually see the random forest also did relatively well than the logistic regression model. However, next we need to visualize the AUC ROC curve. So we did have a very good AUC ROC score. Some of them were 100, some of them were 96, 99, thereabout. Then the next phase is for us to deploy the model. So you usually deploy the best performing model. You saved it using the job lib, and then you could be able to serialize it, and then you dump it into a container or any other thing that you use for you to be able to deploy it. So in other words, you will see clearly that in the real world you may not have this impressive performance. It may go up or go down depending on the problem you're looking. However, but these are the steps that you will require in order for you to be able to perform a supervised learning problem. If you are interested in this content like this, I would be dropping this particular script in my GitHub link, so you could download it from my GitHub link and run it in your PC. Now again, the best way to do data science is for you to be able to run these practical examples. You cannot do data science by studying it. You have to practicalize it. You have to run it, else you cannot be able to know it. So I hope to see you next in my next post. And again, I am always here, desperate to see you succeed and desperate to see a better version of you. Thank you, and bye bye for now.